Hello everyone, thank you for joining today. We are going to continue where we finished last time. Just to give some context, we've been solving this Haskell course, but we've been doing it in C++. It's a pretty good introduction to functional programming, and it kind of gives you the foundational introduction from basics. Why functional programming is good, what tools does it provide, how to use it, but C++ actually came pretty far. There are lots of features there. Um, and it means it now actually really possible to do all of this stuff in C++. In fact, we're exploring how possible, how good it is, and it's a bit of adventure for me as well. I haven't actually went there, finished all this course in my free time, and then I'm like doing it again with C++ with you. No, I'm actually doing C++ with you for the first time. I mean, I did it in Haskell 10 years ago, but a lot of things change in 10 years. 10 years is it's a pretty long period of time. Anyway, the stream is kind of like interactive, even though I will upload the recording to YouTube later. Um, Now you have like exclusive opportunity to kind of ask any questions, like contribute with whatever you want. Hey, oh hi Gren, you made it. I know it's pretty late in Indonesia right now, but kudos for making it. And thanks for joining. Hey, hello. Always nice to see new people. So let me actually just start. I mean, I know you like looking at me, but we actually came here for functional programming. That 10 a.m. here. Yeah, 10 p.m. Okay. Yeah. 10 p.m. I usually sleep. So really good. Really appreciated that you're making it, even if it will be the only time. It means a lot. Even more reasons not to waste time. Let me just jump straight to it. Um, So this is the course I've been talking about. This is like SIS 194, Introduction to Haskell, Spring 2013. There is another version of this course, which is like 2016, but we are starting with this one because this is the one that I actually solved. And we are going to do lesson assignment. So we finished the first one. It's published on my YouTube. We started the second one. The first part is done. It was a bit like the annoying part is done. Now it will be more like functional programming. So we've been doing this algebraic data types. We've been modeling them in Haskell, and we've been writing this single function. So yeah, we spent about like 2 hours. Writing just single parsing functions. There are better ways to do it, and we will actually look into them, but at least we have something to establish, and the rest should be pretty easy. Um, so what is this? So I actually don't know. To my shame, I never Googled, I just accepted. Maybe it's like a name of um, like some programs. Maybe someone knowledgeable in the chat can actually tell me. Uh, what does it mean? Maybe like unique code of specific program or whatever. But I'd love to know too, actually. For me, it's just the name of the course, and this is how I usually Google it uh, to find it. So here it's not C++, so what you see currently on the screen, it's actually Haskell. Yeah, you can say it's C++ 2056. In about 30 years, C++ will look like this. But no, it's a Haskell. I'm actually using C++ 23. It's like the latest available version. There is new standard C++ 26 coming pretty around the corner. So there are lots of interesting features there as well. And don't worry, if you miss like parts 1 and 2, you can watch later afterwards, but I will give all the context. So anyway, we finished implementing this function, parse message. Not maybe the previous implementation. Now we want to write this function parse string. In fact, we will actually read contents of the file from file, and we will parse them as different messages. Hey, I'm not early. I'm starting at 5 p.m. UTC, isn't it? 5 p.m. UTC. Wait. Oh my god. Something happened. Yeah, time zones are hard, folks. Apparently, I'm 2 hours earlier than I promised to be, but this is actually the time I'm usually starting. It's 4 p.m. my local time. Yeah, I can't believe I messed up time zones. It actually happened to me much more often. I once like bought a train ticket, like that's the 1st of July, and I was there, but apparently I bought it 31st of August. Like I really messed up 1 month. I don't know how it happened. So I had to spend 1 month on a train station, just living there, waiting for my next ticket. It was pretty horrible experience. The question, can you compile this algebraic stuff to WAS? Does it depend on stuff WAS doesn't support jump errors? You can pretty much do this in like any language. So the WASM is pretty flexible. There is no limitation. It's like it's a runtime. And in fact, I would say it's pretty much more advanced runtime than C++ because in C++ just they don't have runtime. You manually allocate memory, so you definitely can do all of this. Like as long as you have JSON and you can like parse JSON and do whatever you think, this is possible. The question is inefficiency, how efficient it would be, but otherwise it should be doable in almost any language. Besides, there are tricks to kind of do this stuff using different features. Is Graham Hutton programming in Haskell a good reference to learn Haskell? So I don't know actually because I never read this, but I know that Graham is a really experienced educator. Like he's really good. He has like several talks I think on computer field like coding about monads and lambda calculus. So he really explains this stuff well. Let me actually just share links in the stream. So everyone, you don't need to Google. I will save you some time. And yeah, you will be able to find all of the code on my GitHub afterwards. Just share it as well. Yeah, I'm doing this work live, and I will publish everything, so you will be later able to find everything here. Don't forget to press this yellow star button. I'll show you how to do it. Yep, this is how you do it. It would really help me. But overall, yep. All code will be available here, so don't worry if you miss something or didn't get. And in fact, it would be nice to actually play with it. So we've been starting really slow, giving people some time to just, hey, nice to see so many people here. So actually, I did some changes since the last time. And the most important change is that I upgraded my C++ compiler. Now we are going to do it properly. Like, it's not limited version of C++ compiler. Now we will have C++ 23 features, all of the stuff. My VS Code finally works. So what we did last time, like we modeled this sum type using variants. So it's like a choice between info, warning, and error. These are like log status messages, and you see that info, warning, and error are just empty structs. Except error actually has something inside, and we did this like a spaceship operator. Now if I hover, I can see this type, like it returns its strong ordering, and this is like what you actually do. So that's pretty good. So we have comparison out of the box. We have proper inline hints. Now we have this record message type, or like we have a log message or unknown, and we have another sum type, which is either message or unknown. So basically, if a message follows some proper format, it's message with like message type, which is our choice type here. a timestamp. Timestamp is just shortcut for int, and string the message itself. And basically what we did, we wrote this like really huge function to parse messages in format. So here are some tests. You see the status here, the timestamp, and the message goes afterwards. But in case of error, there is status. So after error, there is status, and then there is timestamp, and then message. So we parse this message into this thingy. And if it's not proper format, so it doesn't start with status, no timestamp, so whatever, we just return unknown. This is just some message. So one thing I changed is that now I'm finally using print line. We don't need to do this cout, send line, whatever business anymore. We can finally do proper like printing in C++. It is indeed available in C++ 23, and there are many more features we can use. There is like, yeah, as I mentioned, auto. Now we have like some inline things working, and in fact, we have even more things, and I'm going to show them. So this is our function onwards. Actually like onwards drop, because it takes vector, it drops a few elements from the vector, then joins all the elements with a space, and then creates a string. And what we can do now, so we manually allocated the string from this range, but since C++ 23, there is this a nice thing called std ranges 2, and this 2 thing allows you to aggregate the result. And we say, I just want to aggregate this to string. So in fact, our words pipe is now just string, and this is what we need to return. So we don't do this, we just return this, and we even remove. So this is like the perfect functional programming. Is just single pipeline of function calls. We do words, we drop few elements, we join them with space, and we combine back to string. Now this is like the dream. This is how functional programming is supposed to look like. It's like almost one-liner. C++ is not expression-oriented language. We still need to write this return statement, but overall it's pretty nice. So what's wrong with cout? Nothing wrong with cout. Print line is just better. It reads better. It has features like formatting, so you want to have like these operators less whatever multiple times, and it looks more like any other language, I guess. You can say it bridges C++, makes it closer to other languages. Is common, lingua franca, whatever, to do things consistently in the same way. So this is like pipe operator. It's overloaded operator, and it allows to actually pipe things from one another. You can define your own overload and do this composition. In fact, I played a little bit with it to do it with custom functions, but here it uses ranges. So there is this include ranges. This is a C++ 20 feature, and it allows you to create this wonderful pipelines of things. So it provides ranges and views are just lightweight references to whatever data they have, and they describe pipeline of these things, and you can just combine. And this operator works with these ranges to do this stuff. So here you can see we did something similar in another functions. Yeah, we don't define pipe, so pipe actually comes from the library, which is really nice, and it's like proper overload. We don't need to do this. In another function, you can see how we did this split. So we take a string, we split it by spaces, and when you split, it doesn't return you like vector of strings, so stream of strings. It returns you stream of ranges. So we manually converted it to strings. Someone mentioned that it's better to use like string view, and because this is just learning exercise, we don't do string views yet. I don't spend time on this to not debug potential issues and to be careful, but generally, yeah, you need to use string view. And then we kind of consume this pipe into vector of words manually. But again, now that we have all the good stuff, I can just do std ranges 2, and now I say I want vector. In fact, this is really curious, because string, okay, it's just one type, string, but vector is a polymorphic type. It's not just any type, it's parameterized by some whatever, but this thing, it figures out automatically, okay, this is like I get a pipe of strings, and then I can convert to vector, so I will have a vector of strings. It works. So I actually I don't need this like stuff anymore. I don't need to manually consume this vector. I can just do this and remove all of this nonsense. And let's actually make sure that it runs. Yeah, it still compiles, still runs, all the tests are passing, and we can see that it's like does all the stuff. So now we have this like really pipeline stuff, and this is what functional programming is about. Like it's really writing these pipelines, consume data, and transform, like any programming about. So this pipe operator C++ works like the R1. Actually, not familiar with R, so I would say it works like OCaml pipe operator, almost like. Yep. So those are actually not branches. Those, it's like they're not much. They're actually transformation. It's like bash pipe. So if you're familiar with bash, or you run like shell command, you run maybe some cutoff file, and you pipe it to grep to search something, then you maybe pipe it to less to have a like page view of this thing. So this is how it's transformation. So in Haskell, in OCaml, they look kind of like guards when you do alternative. In fact, there is a C++ library that abuses C++ a lot, and it uses this for pattern matching. It's really fun. I haven't read the details, but yeah, it's chaining. Exactly. And yeah, the view itself, it is indeed lazy thing. It does consume things lazy. This is kind of like the main motivation to have these lightweight pipelines that can lazily transform data in consume. And again, if we had string views and all of these things, it could be really, really easy. So it's just a few minor things to improve this code. I'm not going to improve this part, which is really ugly with lots of repetition. It is possible. In fact, I encourage you to play with the code if you want to understand what's going on. Like here, maybe try to improve. There are lots of opportunities here. We will look into parser combinators in one of the previous sections, and parser combinators kind of provide nice framework to parse data. In fact, if you try to manually make this code better, you will come up with kind of really ad hoc specialized parser combinators. We just need one step here, but for now it does work. So let's move on. People ask why I use state qualifier explicitly. So I personally love knowing where things are coming from. So I don't write this like using namespace std. Just brings a lot of junk inside my namespace. And because in C++ you can have like function overloading, like all of the stuff, name conflicts not really work well. I can accidentally create something that looks like something else and troubleshoot issues. It doesn't make things too ugly. So, okay, whatever state string, but it makes them more explicit. But I like explicitness. And in fact, at my job where I work, there are lots of different namespaces. At Bloomberg, we have kind of our own namespace, and it helps to kind of avoid conflicts between like standard namespace and Bloomberg. Like there's lots of code, so lots of C++ code. It really helps, and for me, I just got used to it, and it just makes things more explicit. I see that it's still strings or still views or ranges, and I immediately know it's some standard stuff, and I don't need to like worry if it's like mine or not. And like this state optional, it makes things clearer. It For some it may seem like extra noise. I thought I will be annoyed by this. Surprisingly, I'm not. After some time, you get used to this. You just filter like you train your pattern matching. The question: does pipe chain with ranges compile down to one loop or is overhead? So it is pretty efficient. I don't know full the details. I think the best way to kind of do is to read the implementation and to read assembly, but it is really efficient. And the idea, yes, is to be as close as possible to one loop. I'm not sure if there are like maybe talks. I'm pretty sure someone at CPPCon made a talk and compared all of the stuff, but I would expect this does close to minimum overhead. So in fact, this is what I did in the previous part. We wrote a function like old style C++, like what they teach you on the first session of whatever C++ immediately. And then we did this with pipes. So I haven't benchmarked the implementation, but the motivation here is that you kind of like with pipes, you can iterate faster, you can just transform data, you can write it quickly. And if you realize at some point that it's not fast enough, you really need to write like hand-rolled manual loop, then you can do it. You can just extract one part and do it. But overall, you can easily extract parts of these pipes into separate functions. You can reuse them. So here we reuse digits twice. So I extracted digits into function. I reuse digits again, and I kind of do all of these things. So it's kind of promotes this reusable software, and because it's C++, and because people who wrote it are really smart, it's pretty efficient. So I wouldn't worry about overhead unless you really need like low latency and you can have benchmarks to do this stuff. Yeah, so auto is kind of like letting this thing to figure out. So here's this like function from chars, it returns something. It's loading, but type inference works better, and it basically tells me, okay, this is from char's result. So there are some things how it works. It's not as type inference in Haskell or Camel, but it basically in some sense like for example with whatever range, like I don't care whatever this range, I just know this is range and I just want to transform it to string. I don't really care what the type, it might be really verbose and long. And in fact all of these views, if you start composing them, so result of this will become really verbose type. Here we return just string, but some intermediate types can be scary. And here, especially when you use lambdas, with lambdas you only can use auto because this is how lambdas implements it. You cannot refer to lambda type explicitly, so you just lambdas are auto, and the compiler figures out all of the thing. Okay, so we know how to parse one thing. Let's actually parse the entire file. So let's implement a function to parse file, and it takes file name. Let's do also string, I don't really care. And we need to return a list of log messages. So, I mean, we're going to return vector of log messages. So our choice type, which is either message or unknown message, it's a choice type between message and unknown. And when we parse message, we return log message. So this function, it automatically figures out if it's proper format, then it will return us a message. Otherwise, it will return unknown. Now we want to parse an entire file. So we need to read the file. So let me write a helper function with return string, and it just don't file name, it doesn't own. We can do this again. Probably need to use string views and all of the stuff. Just comments aside, we are going to use these things. Hey, new people are joining. Welcome everyone. Yeah, people have been active. I've been surprised. I'm glad people made to the stream and kind of do the stuff. I hope today we will finish this homework. It's been taking some time, but actually this part, like parsing just one string, and parsing is generally a difficult problem. This was a difficult part. After all, it's just really simple stuff. Maybe not simple conceptually, but I don't expect lots of code, at least from what I saw. Anyway, so to my big shame, actually don't remember like on my fingertips how to like parse file to a string. So I'm actually going to ask ChatGPT and uh, generate all of the stuff for me. So this is um, why AI is really good. Like I don't really care like how to um, like read a file. I know it's like it's a solved problem. I don't know what the details. It might not be the most efficient. In fact, I read that this way of reading the file via stream buffer iterator is not the most efficient way to do this. But it's for now just like exercise. We just need to do something to test and be run. The question like, is the problem difficult or is it difficult to do it in FP style using C++? You mean the parsing problem? The parsing problem is difficult if you do it like somehow. You try to do it functional way, but you do it halfway. So this is kind of like a problem with functional programming, is that to really benefit from functional programming, you need to make two steps. Okay, here we are using like optional, we use monads, so it is like one steps, but you still see this is like ugly stuff. And you think like, okay, I did this thing and it's not really good, so functional programming is bad. But you actually need to add one more step, which is parser combinators. And then parsing with them in true functional style actually makes things better. And this is surprisingly happens a lot of time with functional programming. So people used to this idea that you do one thing and your life strictly incrementally becomes better, like in the gradient descent or ascent, you find the local maximum or global maximum globally, and every step makes your life better. But sometimes you kind of need to do like multiple of the steps. You need to cross the valley of pain, of knowledge, or whatever. And probably if you write something really ad hoc for this problem, it will look less ugly. Like you do some ifs without optionals, maybe you do some expects, length 3 and whatever, but then it's not reusable. You just solved one problem and you cannot reuse implementation for another parsing problem. Parser combinators allow this like nice framework. Again, I will talk about them when we'll get there. For now, just good to have something, just like one function to parse. uh yeah, monads mentioned. Anyway, I think, yeah, I need to include fstream for that. Give me 1 sec. And I'm going to remove all of the checks. Like I don't really care. Binary to avoid new line translation. Interesting. Will it work? I guess we'll see. And I return string of this wonderful thing. Doesn't complain. Ah, I see. Missing bracket. So yeah, read file. We do. Yeah, I'm using underscore file contents. Read file name. And now what we want to split file name by lines, and we want to run our parse message function for every line, and then we want to combine them to vectors. So this is, again, perfect functional programming. I'm going to say, I know what I want to do, file contents. I'm going to do split views split. In fact, we did it already here. We split by space, but now I just need to split by new line. So I'm splitting by new line. Even though I'm on Windows, I don't care about Windows new line because I'm using WSL. This is what we're going to do. So we get this like views, and I want to combine every element to message. Const auto. This should be line. Message of line. So this might not work yet because we need to do this like conversion to string, and Okay, this is the missing part. Now we do the same. We do state ranges 2 and we convert it to vector. So yeah, I was expecting this potential problem. Need to do this, convert range to string. That's fine. Hmm. Okay, maybe because I need to specify type, it doesn't infer. Hmm. Much the function of call. Yeah, parse combinators are really cool. Yeah, about blog. Yeah, I want to publish more things on blog, but blogs kind of requires more investment. You know, I write something, then you need to reread, refine, maybe you need to prepare code. So my latest article about CCL, which is categorical configuration language, it actually took me 2 months to finish because I first wrote a library in OCaml, then I wrote tests like to make sure it works. Then I wrote article, like published and all of the stuff, and also this happened after I rewrote my website, so at least it's been something. But then you format, you try to do these things, you want to make it really good. So articles do lots of stuff. Maybe at one point I will continue, but it just uh, do this thing. If you care about both types of new lines, could you still use split? I think you could. I'm pretty sure. I mean, all of the things implements it. So even though they implement in the standard library, you can actually implement your own split. At some point, we may have a look. How would you write your own split? But um, like you can write your own, even if even if standard function doesn't provide all of the things. I haven't did this, but it should be possible. Let me just fix this compilation error. I promise that we are not using ChatGPT to fix those errors, so it should be possible to resolve all of these issues on our own. But who knows? It might take some time. Relax, take a backseat, chill. So what does it say? No matching function for call to transform. Ah, of course. Usually when you see a read alone error, it means you have a typo. Does it still work? No. Still need. So we technically we can do it in one transform, like, you know, convert a string and pass it here. I guess we can do this to kind of make our lives easier. But the idea is kind of you can, just to show the idea, that you can generally compose all of these things in pipelines. And because they're lazy, it's not going to walk through and do this allocation. It actually will do this allocation. It will move it to this function and do this stuff. But yeah, actually, it is pretty redundant. Um, let's do this. At least the code will be slightly shorter. Oh, okay, now it's not string. Yeah, now it's actually a range, so go back to the previous implementation. Yeah, yeah. Thank you, Goran, for joining anyway. Yeah, you go to church. Good stuff. At least we got the implementation of parsing file working. And aside from me making a typo in like views, you can see that it's pretty straightforward. You split by lines, you transform this function, you like parse message, and then we get a vector of our log messages. So let's actually test it. And by testing, let's try to parse the file and actually print every single log message that we have. trying to do FP in C++ looks painful. Doesn't look too painful to me. I mean, C++ wasn't built for functional programming in mind, but I'm surprised that you can actually do it and it's pretty viable. I mean, these pipelines, to me, it feels like a Camel or Haskell or whatever. Obviously, there is complications that you have to manually manage memory. Functional programming languages have garbage collector, so you don't need to manage memory manually for them. But like, and you can realize things become much simpler. But surprisingly, despite that, I mean, it is doable. So the lectures have some like testing files. Let me just download them. So this is a link for a file. What I want to do, okay, homework to sample log. Okay, voila, this is our log file. Should be good enough. And let's actually use this. So auto log messages equals parse messages from a file, and our file is homework sample.log, and we actually want to print every message. So for const out message in log messages, I want to print line, and we're actually using std print line instead of std cout. It's print line of log message. Okay, parse message, yes. Come on, parse file. Parse file. Okay, we're in the message, so yeah, let's do parse file. Now we're talking. Yeah, so this function std print line, like one of the benefits, you can kind of provide any formatting string. So we can say message is like whatever, and put it in single quotes, so we definitely know what it is, but we just want to print the message. So I'm not going, actually, let's keep it, and it's going to print log message. I'm actually surprised it doesn't complain. Oh, oh yeah, it doesn't compile. So obviously it doesn't compile. So the problem is that here, to print log message, it actually needs, well, how to print log message. Here we can see that log message is our type, which is std variant between message and unknown, and it can print like std variant, but it cannot print our types. So let's actually like write a function to convert our log message to string. So before we can print, we will need to do this. So write log message to string. Actually, I'll just call it just a string. And we are going to write a function to convert our log message. I'll go to this type, to string, just so we can see the type. String, and it takes reference to log message. So the interesting part here is that our log message is a variant type, so it's either message or unknown, and this is where pattern matching comes into play. So we do want to pattern match on this alternative, and we kind of want to do it to decide if it's message, like print message, if it's unknown, print like unknown, whatever thing. And to do pattern matching with std variant, we need to use this function which is called std visit, and visit, it takes the value. So in our case, it's log message, and it takes like a visitor. if you're familiar with object-oriented patterns, the visitor is a kind of like object that visits every potential value, like node in a tree or whatever, and it allows you to do. But here it means that we need to have a special okay, better to show with code than trying to explain and trying to do. And let's try it, call it log message to string visitor. This is a really long S name, but and we are going to just return stuff. So what this visitor does is that it needs to be a structure and it needs to provide operator around brackets. So in C++, like when you call a function, I don't know, like here, you provide argument, you provide you write round brackets, you provide arguments separated by comma and whatever. So in C++, if you have custom structure and it has this operator around brackets, it means it can be used as a function. It's kind of like a functional object. So and to make it sure that it works like with std_visit, it needs to have this like overloaded operator, but for all of the possible cases. And this is kind of like how it checks. So here we see that the error says no instance for overloaded std_visit matches to argument list, and the arguments are const log message. So it means like we haven't handled like cases for this. So let's actually do this. So what we want operator around brackets. This is how we define it. What it takes references to other values. Let's start with a simpler one. Let's start with unknown. This is unknown. We tell that it's a constant operator. It doesn't change values, and we can say that it returns something. So we actually want to return a string. Okay, typo. We actually want to return a string, and here we say, okay, we take an unknown. So unknown is just this struct of this message, and we can actually do something. And I'm going to use the precessor to std print line, which is like std format, but it provides the same formatting string. So I'm going to say std format, and I want to do this unknown, and what is the message? And the message is oh no. Unknown MSG. So this is like kind of programming with functional styles, that you have just structures. You might have some methods to kind of do the stuff like comparison operator. This is because C++ provides it, but everything's kind of public and you have full access to them, and you work through functions. You usually don't provide methods. So the visitor is a special case that does this stuff. So this is what we do. And so we did this for unknown. Now we needed to do for just ordinary message. And so inside message, now it's a record. It has 3 fields. It has message type, timestamp, and MSG. And we actually want to print them all. So here I'm not going to do any like prefix. I'm just going to say like, okay, all of these 3 things: MSG type, MSG timestamp, and MSG. Not the best naming, you know, this classic one, but this is the thing. Now we can print the stuff. It shouldn't compile yet. If you followed what's going on, I know it's hard. It's a really concentrated content, but you might have an educated guess why this won't compile this stuff. So feel free to drop it in the chat. There are some questions about chaining operator. Yeah, so yeah, this chaining is really interesting stuff. So when you actually like do chain, it chains lazily. In this version, I also automatically like create the structure, but if you're not careful, if you create pipelines, there are different lifetime issues that come into play, so you might need to be a little bit careful with them. But because it is lazy and it's pretty nice that it's good. Yeah, C++ really has a lot of these features. But anyway, I just want to make sure that it doesn't compile and the error at least somewhat readable. But yeah, it doesn't compile the way I expected. So the problem is that where I specify MSG type, so MSG type, which is like message type, this is our own choice type, which means we need to do the same for it. We need to pattern match on all of these three constructors and print them. It will be much easier, but we need to do this. So I'm going to write function to string, and even though I already wrote function to string, this is totally fine because in C++ we have function overloading, and we can do the same. So I have log message. Now I have message type, which is the msg type, and now I have message type to string visitor. So we have like function overloading, but we don't have structs overloading. This can be done like in different multiple ways. You can have local structs that are defined just inside the function. You can actually define struct inside the function. You can have like anonymous namespaces. You can kind of try to encapsulate, bring it in different modules, and do them inside, kind of group all of this function. For me, I just want to get the job done, and organizing the code will left as an exercise to the reader if you really want to make it pretty. So let me just call this message type to string visitor. And basically the idea is the same, but now we just work with much simpler structures. So we take info. In fact, because info doesn't have anything, I don't even need to specify its argument. I don't need all of this. I can actually just write it in one line. Say just info. It's actually prints as I. Okay, just I. The same with warning. I just press W, and the same with error. So error we actually need, and will be a little bit more complicated, but let's go with state format. This is error code. Okay, let's not be too cute. Let's actually write it in multiple lines. So now finally, this should work. Now we defined all of the functions, we can print, and it should be able to print our log line. And as you can see in the terminal, it does the job. It prints that our message is in the line, and we see the status code, whatever happens, or unknown. So apparently the last line is considered like as an empty line, and it parsed it. So this is unknown, which is expected behavior, but everything else works, and it's written exactly as we get. So this pattern matching took some time, but see at the end I just mostly copy paste it. It's more verbose. So if you do like in functional programming languages, they have native support. This is like their bread and butter. They do this all the time, so they have much better versions of doing all of this stuff. But overall, like in C++, we rely on function overloading and the fact that the proper constructor will be dispatched to the proper function and do all of this stuff, and now it works. So yeah, now we can parse file, we can print it, and we model it with like nice algebraic types, and we can do whatever other stuff. Yeah, so this visitor pattern is the usual way. There are different modern features, like you can use like compile, templates auto, and if const export, so you can kind of at compile time do this almost, yeah, you do like if on the type and pattern match and do this inside one big lambda. I don't really like it because it's not extensible. Let's say So here it kind of checks for exhaustiveness. Let's say I delete the warning case, and now I have an error. And the error says that, again, you kind of need to learn how to read it, all of this stuff, and extract relevant information. But somewhere here it says check visitor results, so it checks if all of the things are required. Like, so basically these things, it like says it cannot invoke this visitor on warning because it doesn't know how to do on warning. So it kind of checks all of this stuff. Again, at the beginning, you can just copy the error to ChatGPT to see what's going on, but basically this is what it means. Like, it doesn't have warning. So you have some compile time guarantees. If I later go here and add debug, let's say I edit like a struct, debug here, whatever, and I forget to update it because I don't know, it might be a project with million lines and I don't know, then I will get an error saying, okay, it doesn't support. So I will solve the problem at compile time before seeing any exceptions, before anything's happening. So dispatch happens at runtime because it doesn't know what's in state variant. So it just knows what possibly can be there info, warning, or error, but it doesn't know what's there currently right now. So it does happen at runtime. It's nothing new. In functional programming languages, this dispatch also happens in runtime. They usually just have this like integer tag store inside the structure, and in this integer tag it just matches like if whether this integer call corresponds in branch, so it doesn't do anything smart. It is possible to have like a compile time dispatch for if you know at compile time what's inside, but if you don't know at compile time, then you kind of have to do runtime dispatch. Yeah, I mentioned exhaustiveness. Have that green. Does C++ have something like type class or interface now, like ad hoc polymorphism? This is a great question. In fact, in this Haskell course, there will be type classes, and in C++ 20, there is this feature called concepts, and concepts were really inspired by type classes, and in fact, they're pretty much like type classes. They're used for the same things, and like it really feels like type classes. So I'm going to talk about type classes in one of the future versions as well when we get to them. But yeah, now surprisingly C++ even has type classes. For other people, type classes, it's similar to traits in Rust. It's different from interfaces. So some people explain them via interfaces when they explain Haskell, but they're different. I will get to them. Anyway, we now can print all of the stuff, so we verified it works, and let's go to the next exercise. Let me close all of the relevant stuff. Okay, accidentally closed homework. Yeah, no problem. So yeah, we parsed it, we verified it works, and the next part is putting the logs in order. Unfortunately, due to the error messages being generated by multiple servers in multiple locations around the globe, a lightning storm, a failed disk, and a bored yet incompetent programmer, the log messages are horribly out of order. Until we do some organizing, there will be no way to make sense of what went wrong. We've designed a data structure that should help a binary search tree of log messages. So this is a Haskell version of this binary search tree. I'm not going to explain binary trees or binary search trees. I hope you have somewhat relevant background, maybe you've seen it. We will implement it from scratch in C++. I'll just give you like a brief idea. But overall, what it says is that this is our tree, and tree, it's a sum type, algebraic type is a choice, and it says that a tree is either a leaf or a node. And if it's a leaf, there is nothing inside, so leaf is empty. If it's node, it has message tree, log message, and another message tree. So first of all, it's a recursive algebraic data type, which means that the constructor node, it has 3 fields, and it refers to itself. So message tree is the same as message tree here, and this constructor has 3 fields. So this is like left branch, this is right branch, and log message is what we currently have been working with. So this is organized in binary search tree. So note that message tree is a recursive data type. Yes, I said. The node constructor itself takes two children as arguments, representing the left and right subtrees, as well as the log message. Here, leaf represents the empty tree. A message tree should be sorted by timestamp. That is, the timestamp of a log message in any node should be greater than all timestamps of any log message in the left subtree, and less than all timestamps of any log message in the right child. Again, I'm not going to explain like binary search tree, but just to give you an idea. Let's say this is our tree. This is how they usually visualized. So you kind of have all of these things here. Okay. So, and we have some like numbers inside. Well, we have like log messages, but whatever, let's say there's like number 7. And it's like it's a binary search tree if things on the right are strictly like bigger than what's on the left, and that's the value itself, and strict on the left are less. So if we go here, here it should be something like 9 because it's bigger than 7. If we go to left node, it cannot be a 9 here. It's actually a 98. That was still valid. It cannot be like 10 here. Whatever, it needs to be less. Then we go 5. So here it needs to be bigger than 5, but because it's inside this like left subtree of 7, it still needs to be less than 7. So we go here, it's actually 6. And here can be whatever, let's say minus 100. Doesn't really matter. So this is a valid binary search tree. Like I'm not talking here about balancing it, how to keep the structure really small and optimal, but this is the idea. And in our case, this log message has timestamp, which is an integer, and it's going to be binary search tree with this timestamp. And unknown messages should not be stored in the message tree since they lack a timestamp. So this is one thing that I wanted to mention, that we are going to do slightly better than in Haskell. In fact, you can do this in Haskell, but for some reason, maybe because the course is old, maybe because they decided not to bother, they decided not to do this. But it says unknown messages should not be stored in the message tree because unknown message doesn't have timestamp, so we cannot order them by timestamp, and we don't need to store them. But here it says log message, and log message, if we scroll again back up, it's the same in implementation. It's a choice between like this log message and unknown. We rename this log message to message, but anyway, here it says it's unknown, and it kind of violates this functional programming concept of making illegal states unrepresentable. Like here, it is possible to have unknown inside this log message, but our tree doesn't store it. So we're actually going to improve this. We are going to store just the message when we know it. We are not going to store unknown. So let me just copy this thing, and we're actually going to implement this tree, which is like recursive algebraic data type in C++. Let me close the browser, and let's go. I'm just going to keep it here. So same as before, we have two constructors, meaning we will have two separate types to represent them. So first of all, we will have leaf, and again, because leaf doesn't stores anything, it will be like an empty structure. And then we're going to have node, but before we store something there, let's define our message tree. So our message tree, it will be a variant between leaf and node. So this is what we want, but this is what we can't easily do. So the question, is there a reason to do leaf node tree rather than node maybe tree versus maybe tree? So in functional programming, there is this concept of isomorphism, which means that there are actually multiple ways to do the same thing, and it relates especially to data structures. So it shouldn't be surprising to you, like if you go to your job. Oh, sorry for unemployed people. Sorry. Let's say if you go to walk in the park, you can go to the park in a multiple ways. Like you can take one route, you can take another. Eventually, you'll get to the park, and there are different ways to do things. So the same in functional programming, you can do many different ways to do things. There is no real difference. The difference how you work with this type. So if it's a maybe, you will have to pattern match on maybe, like one of these constructors of type. Maybe you can use like monadic properties of maybe and do some things in cuter way, so it could be good. But overall, the idea is to maybe like reuse pattern matching like as much as possible. It might make things simpler. Otherwise, kinda you have to, like, you cannot just work with just tree. So if you have maybe tree, then some functions need to be able to work either with maybe tree or with tree to make sure they work. And because in functional programming languages there is usually no function overloading, so it becomes really messy. It doesn't allow this. So leaf in some sense more pragmatic, but again it's trade-off. Some things become worse, some things become more useful. So we can, so back to C++. If we do node, we cannot do this because inside node we kind of want to write I want to have message tree left and I want to have message tree right, and I want to have my message. So this message is actually this type that actually has timestamp guaranteed. It's not this log message, which can be unknown and might not have, but we're actually going to store this message timestamp. And we cannot do this in C++ because message tree is not defined yet. So it's kind of like C++ requires top to bottom. You have to declare a type first before you can use it, and then you can specify. So we can do like it's an existing type where specialization we cannot easily define. Moreover, there is like more fundamental problem. C++ wants to know how many bytes to allocate for a type at compile time. Let's say here we have message. We know, okay, it's a message type. It requires this amount of byte. It's a timestamp. It's like it's an integer, so this amount of byte, and this is a string. We know string like what it is. So it kind of knows the size of this structure. But if it's like if here we cannot know, like will it be a leaf or will it be like another message tree which potentially can expand recursively, then we cannot allocate compiler cannot know how much space to allocate for this stuff. And this is usually solved by introducing pointers. So and by pointers I mean really pointers. So the standard C++ way to kind of define this tree data structure would be like this, like maybe even like C way or whatever. We have SHMSG, we have 3-pointer left and we have 3-pointer right. So we kind of have pointers. We are not going to use raw pointers. It's considered not the best because pointers, they refer to some memory, like it's on heap, and you need to allocate it, you need to deallocate it, you need to make sure it's properly in proper order allocated. And in fact, this is how would you usually define a standard binary tree in C, like C++ before, just pointer to the structure itself. We won't use it because pointers can be null, and then you will have this if kind of to make sure this is null, similar to the question about maybe thingy in that how to do this. There will be some benefits in doing algebraic way, and I will talk about them in a minute. Oh, hey, Atom Fighter 10101. Thank you for joining. We just started writing the code. We've been fixing all the previous stuff and doing some pattern matching, but now we can do this stuff. So what we want is that we want to, in our variant, I I'll format it like this. So in our variant, we are not going to store node. We are actually going to store pointer to a node. So there are this multiple ways to do this. Either instead variant, we can store pointer to a node, or we can store just node, and inside node, we can store pointers. But for reasons, it's actually more convenient to store pointers inside variant. And as I said, we have multiple options. So when you need a pointer in modern C++, basically you kind of want unique pointer or shared pointer. They are located in the memory module. And the difference is the following. So shared pointer, as the name says, and when you have multiple things that have shared ownership of a value. So you have data and it might be referred from multiple places and they all want this data. And unique pointer says that only one owner of this data can exist at the time. You cannot copy this data, you need to transfer ownership. So this is actually really similar to Rust ownership and borrowing semantics, which means like you have to explicitly do this. So in C++, this is achieved not via lifetimes, it's achieved by deleting the copy constructor. So you cannot copy unique pointer. You can create it, but you cannot copy. You can transfer ownership, and this is what we'll actually do. And the great thing about shared pointers is that they actually so shared pointers actually give you this concept of persistent, fully functional data structures for free. If we wrap it this node in a shared pointer, then we kind of out of the box get persistent data structure, and we can refer to previous version. It's got version data structures as well in some literatures. So we can kind of get it for free. In this exercise, we don't really need previous version. And because shared pointers have some overhead, basically reference counter, we don't want this overhead, so we will keep things lean and minimal. So that's why we will need unique pointer. But there is still problem that this node refers to kind of message tree, but message tree doesn't exist yet. So we need to declare a type before using it, and this is how it's done. So we will say like there is some node structure. We are not saying what it is, we just saying it exists. So here in message tree we can actually say, okay, now we will have a pointer to node. So it's either leaf or a pointer to node. And then we say, okay, node, then our node is a message. It's a message tree left and a message tree right. And here it's not a pointer, here it's a variant. And basically this node is a unique pointer of node. So this is how we defined binary tree. Again, as you see, it's not as elegant as in Haskell. So in Haskell, we had like one line, there is like no deal with pointers, and runtime manages all of this stuff for you. But it is possible to achieve all of these things. So this is kind of our question. Message is this structure, which is just message type, like whether it's info, warning, or error. It's a timestamp, which is just integer, and a string of message. So it's a really plain record. It's really simple struct with just 3 fields, and yeah, we just store it inside. Yeah. So it's kind of like when you want to specify like mutually recursive declarations, you need to declare some of them in advance, then define those that refer to them and define them again. And it's not a big deal. You just tell it exists, and eventually, like if you don't write this, the compilation will fail. It will say, you told me this thing exists, but you haven't defined it. So there's kind of difference between declaration and definition. Here we declared node, here we defined it. With leaf, we declared and defined it in one line, and actually this is what you usually do most of the time. You really rarely work with mutually recursive data types, so usually you can define it just this, but here we tell it exists. And pointer, like pointers are known, like pointer is just like whatever machine word 8 bytes. Pointers always have the same size, and it doesn't matter if this like node like really big or if it's like really small or it's like really nested. Pointers will be the same pointers. And leaf is really simple. I think empty structs are just 1 byte. So this message tree will be really lean variant. It's like it's really small, and this is really nice. That's why we kind of want to have a pointer here and not here, because if we had pointer here, then this will be node and it will be like 3 bytes, and this variant will become much bigger. And surprisingly, for implementation, this is also simpler. So let's go back to our browser. So we defined the data type, and now we need to define a function insert. It takes log message, message tree, and returns a message tree, which inserts a new log message into an existing message tree, producing a new message tree. Insert may assume that it is given a sorted message tree and must produce a new sorted message tree containing the new log message in addition to the contents of the original message tree. However, note that if insert is given a log message which is unknown, it should return the message tree unchanged. So basically this is insert. We're inserting value in the tree. Because it's a binary search tree, we need to maintain proper order of elements inside the tree, and timestamps inside messages define our order. And there is this like requirement that if we insert unknown, then we don't insert unknown, basically, because our tree doesn't start unknown. The declaration of structure before defining it is the same thing that we do when declaring a class to be able to use it as a friend in another one before defining the actual class. Yeah, it's basically the same. You need to tell that the thing exists, and then you define this thing. So because like in compilation there are two different steps, like compilation and then linkage, and C++ kind of makes it more explicit in some sense that you can tell that things exist. You can define it even in one file and declare in another completely. As long as it eventually during link time it exists, it will be fine. So it will be able to resolve all of these holes. But yeah, you need to tell, like during compilation, you need to tell compiler that this thing will exist. Like I promise it exists, you will eventually find it. Okay, so let's actually implement the insert function. And as you guessed, we are going to use pattern matching again. And even several times. And here it will be even more fun because our data type is recursive, meaning that our pattern matching will need to be recursive as well. In functional programming, you will just write a recursive function, but in C++, things are a little bit more interesting. So let's actually do. We will write the function insert. It takes log message. Let's say log message. And it takes a tree. And it returns a new tree. So there are multiple ways to implement this thing. So remember what this like unique pointer business now becomes relevant because it means at the same time you can have only one owner of this pointer. So if we just say like we pass message tree by value, which means that the caller of this function must copy the message tree, but they can't. Like they can't copy because we like have unique pointer and it cannot be copied. You have to like traverse the tree and copy it fully. So here we actually because as I said, like we are going to have only one owner of our message tree, we are going to pass it by reference, which means we are going to modify this tree. And again, if I pass it by const reference saying that you cannot modify it, then it means I will have to kind of create a full message tree from scratch because there is only one owner of unique pointer and I cannot do this. So here we will just modify it. We can just like we can return void. So we are saying we will modify this tree and we don't need to return it, but it will actually be, so like we don't return, we will modify this tree and you deal with it. But it actually will be more convenient to return the tree, and because we are going to move data around, it won't be too bad. So the first thing we need to do is that we need to like pattern match on this log message and make sure that it's not unknown. So if it's unknown, I just want to return the tree itself, like I don't want to care. If it's not unknown, I want to actually insert. So you remember pattern matching, we do this like struct with visitor, and we can use state visit, but the alternative for here, I just don't feel like writing struct, so I'm actually going to write in a different way just to demonstrate the difference. So let me actually Google it. Actually, search for just state variant. Is this like mutable borrow? Yeah, so in Rust it's pretty much like mutable borrow. So so these are kind of functions that we are interested. So there is this function holds alternative that checks if the thing is inside the alternative. And there is this function getIf, which obtains a pointer to a value if the thing has what's inside. So with getIf, there is this like nice example. Apologies for the noise outside. Apparently we've been doing too much functional programming in C++, and I don't have a license for that. They're on to me, so we need to be careful and wrap up the things really fast. But anyway, with getIf, kind of what you do, you pass a reference to a variant, and it returns you a pointer to the thing inside. Like if it's you actually say I want int and it's pointer, and it will be like null pointer if there is nothing inside. Otherwise, it will be like whatever thing. So this is what we want to do. Because I don't want to write visitor, and this is how you can do like alternative to pattern matching in C++. If you don't want to write visitor, you just want to have like really quick and dirty pattern matching. For some things it works. So anyway, yeah, and I need to dereference it. Let me do this. So if log message getIf, I want to say unknown. So inside log message there can be unknown, and I need to pass reference to log message. And because this returns pointer to unknown, you can see it in the line. I will say unknown pointer unknown equals. So in C++ I can it's almost kind of like if let actually. Oh, let if I don't remember. Like in Rust, there is this feature when you can kind of pattern match and get the thing. Yeah, and this is like const pointer. Yeah, we cannot modify the thing, so it's like a const pointer. So if we inside have unknown, then we don't do anything. We just return tree, like we don't modify it. And here you can see that like, yeah, this like function, whatever, like it's a deleted function. We cannot return tree because here it will actually copy. So with the way it's written right now, it will actually do the copy of the tree, but we are not allowed to do this. So what we are going to do, we're actually going to move this tree. We are going to say, okay, we will actually return this new tree, and you cannot use the previous one. So in Rust kind of has this compile time guarantee that you really cannot use the old one here you can still kind of still accidentally use this, so you still need to be careful. Yeah, but overall, this is kind of the general idea. So we can move it, meaning that we transfer ownership to the caller, and then you kind of call it and have only one thing at the same time. So otherwise, like it's not unknown. It means that there is like a message. So we handle this case where we don't insert tree. Now we know that there is a message, and we extract message. In fact, it is actually encouraged to use auto here, so you don't duplicate like thing. Otherwise, like if you have some inheritance, if you have polymorphism, you can accidentally get wrong result. Like here, you already specified that it's a message, and if I hover over auto, it says it's message. So the type inference works, and like it will be actually really cleaner. So we extract the message, and this is the problem with this if approach, because let's say if later I go to log message to this variant between message and unknown, and I add something else, like this will crash. This will like crash, because I will get like null pointer. I'm going to do like some really bad thing with this, and like I'm going to dereference it, and yeah. It's not going to grade good. So that's why this like visitor instruct is better. Here I'm just showing an alternative, and because I'm being a little bit lazy, I'm doing this stuff. And I'm actually going to return insert of this. So now it's not unknown, now it's message, and I'm dereferencing message, and I'm doing this tree. So this insert will be function overload. Now not to log message, but to message, remember, because we store just messages. We still return tree, and so I just split this function in two functions where I insert message and I do this pattern matching on unknown message. And now this is function that actually inserts the real message, and this will be like a kind of like a recursive function that does the thing. But remember, like message tree is this algebraic data type. I need to do pattern matching, and it means that I need to, now I want to do it properly, and I want to have like a visitor. So I'm going to say struct insert visit, and whatever the thing inside, it will insert the value inside the tree and return to me. So what I actually want to return, I'm going to visit with this insert visit. I'm creating the value of insert visit inside tree, and I will return like the new tree. So this struct, you see, it's like written before this function. So by definition, this struct doesn't know anything about this message. Like how does it know what message to insert? And this is kind of like another trick. If you wanna pass something to this visitor, you can just store it inside the struct. So in our previous functions where we did this visiting, we just converted value to string. So let's show me this one, it's simpler. We didn't need to store anything inside. It's like really pure function. It depends only on the value itself and returns the value. But here we have like another value, and we are going to store it inside our visitor, which means here going to have MSG stored inside, and I don't need to write constructor. I guess in C++ there is this feature of aggregate initializers. You can, if you just have standard aggregate type, which again, if you program in functional way, all of your types will be standard aggregate. All of these types, node, leaf, whatever previous, all of these aggregates, we can just specify what we want to have inside. And now we actually need to do all of this business with operators. So message tree operator, and what it takes, let's say we're working with the leaf. We want to insert inside the leaf. It is going to be a const. So this const actually kind of almost important, because we are not going to mutate this message. We're not going to change it. We are going to refer to it. So if we want to, okay, let me write all cases. Because it's a visitor for this message tree, it needs to handle all of the cases of this message tree. So it's kind of like leaf or unique pointer to node. So it means that the second constructor will actually accept unique pointer to node as a reference. We'll call it node. And again, I cannot pass it by value, because there is only like should be one owner. We will pass it by reference, and we will return a new message tree based on the value of this node. And because we are going to mutate it and do all of this stuff, we're just doing the same thing as here. Just kind of transferring ownership, but it's really cheap, because transferring ownership is just convincing the compiler, like, I don't know, I don't own this thing anymore, like, do whatever you want with it. And yeah, we are going to mutate this, even though it says const, but const doesn't allow to mutate its fields, but still allows to mutate arguments, which is a thing you need to know. Okay, anyway, we're trying to insert MSG inside leaf. So leaf is an empty tree, and it's really easy to insert inside empty tree, because there is nothing there, which means you can kind of just create the node itself, and you don't need to do anything. So this is what we are going to return. We need to return message tree. Message tree has two like constructors, still unique pointer, or like for node or leaf. So we cannot return leaf, but we need to return unique pointer. And to create unique pointer, we are going to create function make unique, and we will tell what's the value. So we are returning make unique of node, and now we need to provide arguments of the node constructor, and it takes like message tree left, and message tree right. So message is our message which we store inside, so we can easily create this. So because now we need to provide left and right, but because it's a leaf, there was no left and right, which means we need to kind of create something. But there will be also just leaves, like the empty trees. We had the empty tree, now we inserted one thing, and we just create two children with really nothing. And because it's like this like left and tree, and they're not pointers to leaf. Actually, I don't know why I did this. I can just say this. So here I created unique pointer node with message, and left subtree is a leaf and right subtree is a leaf. So this is how we insert it inside the leaf, and we return message. So here we constructed new pointer. We don't need to do any moves or whatever. We just get it. So like again, C++ compiler is really smart to figure out that like you just construct it, you return it, like you don't need to move it, ownership, you just materialize it all out of the air. So this is great. So this case is more interesting. Now we want to insert a node, and there may be multiple cases. Again, we want to maintain this property of whether it's of binary search tree, whether the value is bigger or smaller than the value inside node. So we're starting with if. So if what's inside node message timestamp. So again, because it's a pointer, to access a member of a pointer, you need to use arrow. But now MSG is not a pointer, just value accessed member with a dot. Again, a few things to keep in mind. So if this timestamp is bigger than MSG timestamp, actually, let me do reverse. My brain thinks in this way. So we want to insert this message. If its timestamp is smaller than message timestamp, then it means it needs to go in the left tree. And we are passing reference to a node. It means we can just say that the left tree will be something new. So this is why we actually return message tree. This is to do this trick that I can say node left. Now please insert like this message to the left tree. And this is where we recursively want to call ourselves. Like I said, I want to recursively insert into the left tree. But remember, this function insert, it's below us, so I cannot just call insert. I can again define it first, and then I will be able to call it. But I can just copy this visit, and I'll say, okay, please visit with the same insert visit like myself inside tree. But what is insert visit? Insert visit is ourselves. So we don't actually need to create another structure of insert visit. We can just say, please use me. Like, I'm the visitor for this, like I'm the danger. I'm the visitor for this thing. Just use me again to insert and left thing. And now we don't need to actually pass this message recursively, which is a nice bonus. So this stored only once inside. You don't need to kind of store it again. It will automatically figure out and pass it, all of this thing. So it will, this is how saying, please use me to recursively insert inside left, and it will do the same thing. It will kind of use this operator, and if our left child is leaf, then we will just create new node and we will insert. If there is not leaf, if there is another pointer, then we will again pattern match on this. So let's do else. Else if message timestamp. Let's do. Let's do a little bit prettification. Let's name our current timestamp. Like, technically there is nothing wrong with referring to the same field months. It just doesn't look elegant. It's not difficult to create a temporary variable, not costly. So anyway, if timestamp is bigger, it means it needs to go not in the square hole, but in the right subtree. So we basically do now right, now visit use me and insert in the right. So if it's smaller, go to the left. If it's bigger, go to the right. And then, so we updated this node, we updated its either left or right tree. So we didn't update the tree itself. So there's kind of like this implicit behavior. If this somehow a new timestamp, which is exactly what we have in the tree, then we will just ignore it. Again, whether you want this behavior or not, you can like put bigger equal here or not, but I think for this implementation it will be fine. So otherwise we just return our node, but again we cannot just return it because we cannot copy it, so we just move it and we transfer ownership to this node. So this is like pretty elegant and like small, pretty elegant and simple implementation of recursive. And remember, not anywhere I deal with null pointer exceptions or null pointers, because I defined it this way algebraically. So there will always be leaf on node. That's why I can just pattern match on leaf. I don't need to check whether it's not null pointer or not. By construction, there always will be something, and here like I'm passing this stuff. So I explained all of this wonderful code to you, but you know, a single compilation error worth multiple things. Unused variable unknown. Interesting. Yeah, technically here, because I don't use variable, I don't need its name. Can I just do this? Wonder will it work? Yeah, nice. Almost like functional property imagine when we don't care about the variable name, we just put underscore into it and do this stuff. So yeah, basically, is this node a parent? I don't know what node they're talking about, but this node is kind of like our current node. We are starting with the root of the tree. So here's the root of the tree, and we are going to the root, and basically we are updating left or right node depending on the condition, and the code compiles, as we can see. Yep, so that wasn't as painful. It's almost like pattern matching, maybe not as, again, not as elegant as in functional programming languages. It would have been fewer lines, but again, considering that we have like proper ownership semantics, we are doing this like with types and stuff, trying to be careful with allocations and use this stuff. There are like a couple things can be done better. So like you can even avoid the final last copy of message, I believe. You can just if you do properly, you can do move here or something like that. So it would be really, really nice. So it's a minor, but you can do all of these things, and it's really nice. So we implemented this insert. Let's look at what's next in the menu. So once we can insert a single log message into message tree, we can build a complete message tree from list of messages, specifically define a function build and insert like this. Like means we have a list of log messages and we want to build a new message tree from this list, which builds up message tree containing the messages in the list by successfully inserting the messages into a message tree, beginning with the leaf. So basically we inserted one thing, one log message into message tree. Now we want to insert multiple things. And again, this is like really easy to do in a functional way if you go back to the code. But you have to handle the equality case. Bigger should be bigger or equal. Yes, I mentioned that. So I think in our case, all timestamps are unique, so we don't have to do this. But yeah, definitely you can have bigger here, or you can have less or equal here. Or you can have separate equality case and do override depending on what you want. Again, this is a training exercise. I don't think it really matters what to do, but yeah, in practice, you need to figure out this pesky detail. So message tree build, we take list of messages. Let's do vector log messages, and we return in a single message tree. So here, actually, I'm arguing that this is a one-line function. If we use another functional programming feature available in modern C++, specifically, I'm talking about fold left. So in std ranges, there is this fold left, and like the way you use it is that actually in documentation here, it's like left folds the elements of given range, and it returns the result of relation in the chain expression f init x1 f of init functional programming init, am I right? So f of x2 and so on. So basically it takes this function. So here to fold, you pass a function, you pass the initial value and the like range, whatever you want to do. And it applies this function again and again, starting from initial value and the first element of your collection. Then you get the result and you pass it to the function itself and to the second element of collection and so on and so on. And like there are some examples how to do this with pluses, but actually this is exactly what we want to do to build a tree. We want to take a log message and we want to take a tree. We insert this message in a tree and we get a new tree. And then we take this new tree and we take another log message and we insert and we get a new tree. And we want to repeat this process again and again unless there is nothing left. So I'm going to use fold left. Let me double check. It's in the algorithm header, so it's not in the ranges. It's actually inside algorithms to be available. And it takes 3 arguments. So first of all, it takes... Wait, what does it take? I always confuse the order. Yeah, so the first argument is the collection. This is our messages. The second argument is the initial value, and we actually have a natural initial value. So our empty tree is like kind of natural initial value. We get an empty tree, which is just leaf, and we start inserting messages into this leaf. And if you remember, the first time we will insert into leaf, we will get a new pointer and whatever, do this. And here we want to pass a function how to insert. So we kind of already have a function insert. I don't think it will work directly as it is. Yeah, I need to change the order of arguments. Let's try. I haven't tried it. So let's change the order of arguments in insert here, and let's just pass insert. Yeah, I was afraid so. So this is like one limitation of functional programming. It's not always functional in C++. So this requires like actually a struct, but no big deal. We just create a lambda, and the first is accumulator, so it should be message tree, and let me put it on a separate lines tree, and then the actual log message. Specify constraint. What we want? We want to return insert of tree to. Yeah, now it compiles and now it works. So yeah, basically what we do is that we use this for left, we iterate over all messages, we start with the leaf, and here I just tell, please insert this like message into the tree. And it actually works with our like unique pointer and all of the stuff. Actually not automatically, I wasn't sure why, so I checked the implementation, and apparently the implementation is really smart. Let me show you this one thing. I mean, it's functional programming, but we're still doing C++. So this is possible implementation of this thing. And here, like when it updates accumulator, it actually invokes the given function and it moves the accumulator, meaning that if you have something like unique pointer inside, it will move and it will work. Like it will be like pretty efficient. That's why like smart people wrote this stuff. They thought about this case that maybe you want to build a binary search tree from unique pointers in algebraic data types while you're solving a Haskell course. Yeah, they thought about our stream right now and they did this thing, which is really cool. So thank you for them for this. Made my life easier. Yeah, but now we have a this build function. This is basically how it needs to be like function. We just fold, and you don't need to care about indexes like iterations, vectors. You can just do in a functional way. So yeah, this is a build function, and okay, let's do next. Finally, define this function in order, which takes a sorted message tree and produces list of all of the log messages it contains, sorted by timestamp from the smallest to biggest. This is known as an ordered reversal of the message tree. With these functions, we can now remove unknown messages and sort the well-formed messages using an expression such as in order build tree. Note there are much better ways to sort a list. This is just an exercise to get you working with the recursive data structures. So yeah, if you're familiar with the stuff, there are like different traversals of a tree, like in order traversal, pre-order, post-order traversal, and this is like a traversal where we want to like just basically print values in a sorted order. So let me actually call this an in order visit, and already know how it goes. So now you kind of see the patterns. If you want to do some work on algebraic data types, you define a function, call it in order, it takes just tree. In fact, now we are going to take it by immutable reference because we are not going to own this tree. We are not going to discard it. This is like we are just traversing, but we still want to use it. So we are not going to update, we are not going to update it. We want to take it by immutable reference, by non-owning reference. And as a result, we want to return a vector of log messages. So let's actually do this. Let's do set vector of log messages. And here we kind of want a slightly more interesting visitor. Our previous visitors, they updated data or produced new data, but now we kind of want to accumulate some data. So in functional programming languages, you work with linked list, and you can just add elements in the beginning and the end of linked list. But here we kind of want to be more efficient. We need to create a vector. And what we are going to do, we are going to create a vector. We are going to store this mutable vector inside our visitor. And as we visit our tree, we are going to update this vector. So this is what we are going to do. So state vector, actually, let's do this. So inside our in order visit, we are having state vector of log message, MSG, and call it messages for explicitly. And I'm going to create a visitor, which is in order visit, and I'm going to create just initialize it by standard vector, by an empty vector. I mean standard. So this is the visitor, and the step inference is correct. And now I'm not going to return anything from this visitor. I'm just going to call it. So I'm visiting with this insert with my visitor, with my existing value. Visiting the street. So now it's we are not going to return it. It will be just simple void, and I will return what's inside the visitor messages eventually. So this is kind of like one way how you can accumulate results. You just store something inside and you return. So it will copy the entire vector. I cannot easily say if we can do just move, because it's a local thing. So let's just copy the data is small. I will think about it after that. So anyway, the pattern is the same. We have this like message, we have this like operator overloaded for leaf and for unique pointers, but now we are not returning anything. So we'll just say it's void. And for leaf, we don't do anything. So actually, because when there is leaf, we don't add any messages. We don't have any messages. But when it's a node, so what we need to do, let me remove this stuff, the distractions. So we need to visit the left node. We want to add the current node to the messages, and then we need to visit the right node. This is the definition of in-order traversal. So let's do exactly this. Again, we are using us as a visitor, and I want to visit the left node. I want to visit the right node, and just between when I visit them, I want to add to messages the current value. And this does not compile for two reasons. So first of all, it doesn't have, so the types don't match because message is just message inside my visitor, but here I need to return a log message. Let's make our life easier. Like, why do we need to cast to an upper type? Let's not lose this knowledge, the fact that we have messages. Whoever wants to deal with them, they will deal with them. So there is another reason why it doesn't work, is that let me see. Yeah, so this const kind of makes things harder because now it's actually not a const function. It actually mutates our messages. Sure, it's like short-living, but it's still const. We don't need it. But at least, hey, now we have a proper in-order traversal of our tree. It doesn't compile. Let me figure out what's wrong. Maybe I need to remove this const from everywhere. Yeah, I was hoping this looks like software dev, not the first 1% of code tutorial like the rest of the stream in this category. I don't know what it means. Sorry, I'm not reading after 2 hours of hardcore functional programming. It's hard. Something doesn't really match. So this visitor doesn't like this visitor. No type named type instruct. Huh? Oh, delete. Instantiation of state visit. Huh? Ah, yeah, I'm passing by reference, but I'm not actually modifying it, so it's better to pass it by const reference. Yeah, don't ask me how I figured it out. It's magic. After some time, it's like wipe C++ coding, but in the old definition of wipes, like you don't use ChatGPT for wipe coding, you just feel it like at some point of time. Like C++, you think C++, and everything just become natural. So this is a much simpler thing. Anyway, one last thing. So exercise 5, which is the final one, is to like we have decided relevant means errors with a severity of at least 50. Write a function which takes unsorted list of log messages and returns a list of the messages corresponding to any error with a severity of 50 or greater, sorted by timestamp. For example, if we have this log, which is I think which is our sample log, yeah, then at the end we should have this result. So this is actually where functional programming kind of finally starts shining, and we can implement a final pipeline. So let's say void what went wrong, and this will be like a full function which takes file name and it does all of the things we did before. So ideally I want to use this pipe operator to kind of pipe functions nicely, but like because pipe work only for ranges and I don't want to bother with writing my own overload, then I'm just going to do this old school style. So let's do this file name. We're parsing file name. Now we're just writing glue code. All of the smart stuff that has been written, that can be written, and even the ones that cannot be written, it is already written. We just need to build all of this together. So this is our log messages. Now we want to build a tree from these messages. So we are saying auto tree. We are building them from log messages. Types are correct. I'm type inference maxing at this point. Like I don't even bother with types. So I'm saying that just messages. Let's call it relevant messages. If this is in order of message tree. So we parse messages, we create tree, we filter out all unknowns. Now we sort them. And now what we want to do, we just want to print all of the messages. So now we can use the ranges again. So let's say auto important messages are the ones that yeah, I mentioned about string view at the beginning. I'm not using string views because they require thinking about lifetimes. 100% CPU of my brain thinking about functional programming and how to explain it. There is no space left for thinking about string views. But generally, yes. So we have file name, and file name can be string view, and then itself the file contents. Ideally, maybe we don't want to copy file contents, but you also don't want to store the entire file contents in memory. So thinking how we can refer to regions and how to do this stuff in parsing is good. But yes, ideally you want to use string view. So important messages are the ones that are error and have severity 50. So what we're going to do, we're going to do relevant messages. Now back to our friends views filter. I want to do slightly more interesting thing. Let me one second. I'm trying to figure out if there is a standard function like this in C++. I want to map and filter in one, which is in OCaml known as map filter. In Haskell is known as map maybe, and something like in Rust. I don't know how it's called in Rust actually. Yeah, apparently it's available, but maybe too early for our time. Yeah, yeah. I don't like it, but whatever. Okay, so first of all, we need to filter all of the things that have errors, and the priority inside errors is bigger or greater than 50. Yeah, I want map maybe. Unfortunately, not yet. Ideally, we want it. We can write our custom map maybe, but I'll basically write it just here. So yeah, let's not bother. Anyway, what I want to say. So we are going to do filter of const message msg. So I want to check if there is if it's like an error, and if what's inside errors has and then the priority is bigger than 50. So we are going to do a very similar thing we did before. So in our MSG type, we want to extract error. Now we are going to actually use it. And if we extract error, then I return that error code is bigger or greater than 50. Otherwise, I return false. You're not interested in all this stuff. And yeah, because it's a pointer, we dereference it like this. Hey, Scott, you joined just in time. We're almost finished. Give me 10-15 minutes. I just need to finish this one last thing, and it took a while, but you know, it's one thing to solve the exercise and another thing to try to explain it. Okay, so we actually filter all of these messages by important priority, and now I want to transform, and I want to return only the things inside those the messages inside those log lines. When transform, then const message msg, and then just return msg. And this is like, it's our pipeline. And when it was like some discussions in the beginning that this is like lazy. So at this point, when I created this pipeline, nothing happens. Like I'm staying here, like on this line afterward, nothing happens. It just created the pipeline. In a sense, it created the description of how the data will be transformed when you start consuming it. Now I'm not yet consuming it. I'm just created the pipeline. One way to consume it is to actually like use a for loop. I can say, because I just need to consume them only once, or to something like that. MSG in important messages, and it should properly infer type as string. Yeah, it infers proper string. And I'm just printing the MSG. Again, we're using print line, no more cout. We are proper functional language, and here I just do what went wrong, and hopefully we will see after all of this suffering the expected result. And yeah, way too many pickles, bad pickle flange interaction detected, flange failed. I think this is what we wanted. Way too many pickles, bad pickle flange interaction detected, flange failed. Yeah, we did it. Yeah, so we can comfortably say that we implemented this exercise in a functional way. We used pipelines, we use algebraic data types, we use pattern matching, we use unique pointers. I elaborated a bit about how we can use unique pointers or shared pointers, how this problems with like null pointers or using leaf explicitly. You see our code becomes elegant. There are different ways. So we looked at different types of visitors actually inside one exercise. There was simple one like toString. We don't need anything else. We just return string. A slightly more complicated where we pass the same argument over and over recursively to our function with MSG, and then where we accumulate our results with in order visitor, and then we were able to finally pipelines. So maybe it looks like a lot. I generally don't think it's hard to write. I just think in terms of pipelines and transforming the data. But obviously, when you write code, you don't explain it to other people, so you take it much faster. And once you get used to this type of like writing code, it becomes quite natural. Must feel nice when range code compile and first try. Yeah, I mean, when I work like with OCaml or Haskell, there's like types, proper simple types, and people usually complain, oh, but I don't want to run type inference engine in my head like all of the time. Like I just want to write code and compose it with things that make sense. I used to say that no, you need to run type inference engine in your head, and it's actually pretty easy to run it. But I think maybe because I like spent many years writing functional programming, I don't run it myself either. I just use it by examples, and this is what you do. Like when you write enough of this code, it just becomes example, intuition driven. Like you just kind of know what to do, what to expect. You be careful with like lifetimes and all of the things that things can be misused. But overall, this is how you do. And we also haven't used anything like really clever with ranges. So we haven't even written our own range. We haven't used like complicated. And you should have joined the previous week stream where we had some problems with ranges and some unexpected things. But overall, just got here. Please start over. Great idea. In fact, I'm going to upload this entire recording to YouTube. I wrote in my tweet that I'm going to upload 2 hours of C++ content. I think it's more than 2 hours. So people will complain it's too much. I mean, people complain about Theo uploading 40-minute videos. I don't know about 2 hours, 2+ hours of C++ content in functional programming. But anyway, you can watch it. Thank you all for joining. It's been really fun. I really enjoyed lots of comments in the chat. Lots of first-time people joined in the chat. And it really means a lot to me. Your support is important. Obviously, if you have any recommendations, what you want to see, feel free to let me know. I am planning to finish this course first, but after that, my agenda is free, so I'm fully available. And you can let me know what you want to see. So, because after all, like, I like just talking to myself, but if I wanted to sit for 2 hours and talk to myself, I probably wouldn't do any stream. So if you're interested, let me know. I'm always happy to hear what people want. The next stream will be in a week. So for now, I'm just doing the same time. How we learned not 5 p.m. UTC, apparently we learned it's 3 p.m. UTC, and there's maybe some time zone will be soon. So the same time on Saturdays every week for 1 or 2 hours, depending on how complex it's going to be. So the next time, the next homework is about recursion patterns, polymorphism, and prelude. So there probably will be some more recursive functions and do the stuff. Should be easier compared to what we did. So I would say this is pretty hardcore. So for functional programming, algebraic data types is a simple stuff. You just define, you do pattern matching. It's for LS9, but in C++ a little bit more involved. But overall, like, you just get used to it. Like, you know, you have struct, you have this operator overloading, you know, you have the state variant, simple stuff. You just learn a few rules and then you get there. Advent of code in December. Yeah, Advent of code in December. I'm not sure if I can do stream every day with solving Advent of code, especially in C++. Maybe I'll do it in OCaml. In OCaml could be simpler. I'd like to see you write CPP syntax to more like Haskell-like. So good news for you. The entire code will be available on GitHub. Feel free to run like ChatGPT or Claude Sonnet 4 or Copilot if you're really brave on that code and see how it will look like in Haskell. I'm pretty sure they should be able to handle it. Let me know it. But overall, yeah, thanks for joining. And I guess see you next week. I'm going to enjoy my dinner after 2 hours C++. I think I enjoyed it. And yeah, see you.